let's start the second part related to the smart transformer. So yesterday I gave a general introduction of why actually we think that it might make sense to improve the electrical distribution grid with these more intelligent devices. Then I discussed a bit about the hardware solution, so how we can build one of these, how people in the past or actually in the present are thinking to build solid-state transformers. And I've also put this focus, the spotlight on the services, because we are talking about very complex power electronics equipment. It means expensive. It means probably less efficient than a normal transformer. So the way that we can sell it to the customers is that this is an investment and it brings services to the grid. So the smart transformer can actually help solving many problems of the electrical distribution grid caused by renewable energy, loads, in displacement between production and consumption of electricity. So if with the smart transformer all of these can be solved, then it is very, very worthy to study and to invest it and to deploy it into the electrical grid. So once we have the hardware of it, then we need the control. Yesterday we saw some examples on how to control, for example, the low voltage DC to AC, and also a model for the DC to DC converter. So for today, give some general overview on some control implementation, very general because I still have many slides as you saw yesterday, and I can talk about the control quite a lot. But the goal is to show how these controls can actually help in doing something good for the electrical grid. So, as a general idea, we are talking about a three-stage solid-state transformer with medium voltage DC and low voltage DC available. Because we are thinking that this is for the future DC distribution grids, we need to make sure to have the compatibility. And in the case we switch to a complete DC distribution, both medium voltage and low voltage, then the inverter stages in the medium voltage and in the low voltage, maybe they are not necessary anymore. But it still is, as long as it provides services to the grid, it still is a smart transformer. Okay, this is the block scheme that we saw yesterday during the exercise. And as it is right now, this is simply one of the several possibilities. It's simply like a proposal on how we can actually control a structure made of 3 stages of power conversion. So let's consider the stages separately. The medium voltage converter is interfaced to the grid, so we can think that we can control it as a normal, say, grid-connected converter. So we will have some current control. Usually, once we are talking about distribution, we are interested in power control because for distribution, once we want to provide services, actually we have requirements for active and reactive power. But again, we're still talking about current control. Then, it operates as an AC to DC rectifier. Again, rectifier or inverter, there is not much difference. It's just that the sign of the current is different. So we can think that after inner current control, plus the phase lock loop, plus everything that we need for a grid-connected converter, we have an outer loop that controls the DC link voltage. So by controlling the active power exchange with the grid, we charge, or anyway, we control the voltage over the medium voltage DC link capacitor. So up to now, it doesn't matter what I'm connecting here. It could be a medium voltage drive, it could be a resistor, because this stage is totally standalone. The goal of this stage is to control the current, eventually providing services like reactive power support to the grid, and then regulate the medium voltage DC link. Now, DC-DC converter. DC-DC converter, there are so many DC-DC converter proposals on the internet, so we have really a very vast literature on how to control it. If we are thinking of a dual active bridge, for example, we have many targets. Maybe we want to control, I don't know, the power, maybe we want to control this DC link voltage, or maybe we want to implement some other advanced control for, I don't know, rejecting the disturbance in the medium voltage or low voltage DC. All of this is like the next stage. Let's just think that for a DC-DC converter, if we have under the assumption that the medium voltage converter is regulating this DC voltage, the goal of the DC-DC converter is to ensure that whatever happens here, the low voltage DC voltage is controlled. So it basically operates as a standard DC-DC converter like the ones that we are very familiar with. Let's just think of a battery charger for the laptop, for the mobile phones. Basically, it needs to control some output voltage, 5 volt, 10 volt, regardless what is happening at the input voltage. So, control target is the low voltage DC link. How do we do it? Well, in the case of the dual active bridge, we have the possibility to control the power exchange. Dual active bridge is a very nice converter because of the principle of operation by controlling the phase shift. There is a power equation, so we actually get already the power, open loop power control, basically. So by changing this phase shifter, or anyway the control variable if we have another DC-DC converter, we can transfer power to the low voltage DC link. Again, this is just the basic thing. And thinking to have a power flow controller, we can think that we can have a maximum and a minimum power transfer. We will see what this means in a few minutes. Then, for the DC to AC, so what we saw yesterday, the main task is to co-regulate the low voltage AC network to make sure that whatever we connect to the low voltage AC network, we have some stable supply. And already this is a serious improvement compared to the standard transformers, because one of the biggest problems of the actual distribution grid is that the transformer, they have an impedance, the series impedance of the transformer. So if we connect something different, if the load increases or decreases, then we have the voltage at the point of common coupling, the voltage of the grid goes up and down. Standard transformer, they have a mechanical variable turn ratio or multiple taps, so it's like tap changer, electronic tap changer, that basically can change the voltage in discrete steps to compensate for this load dependency. But actually, we are talking about power electronics. So controlling a voltage at a specified point is not that hard. So we just need a controller that has an open loop infinite gain at that specific frequency. So something that is natural for power electronics is not for a conventional power transformer. So already this is a major improvement and a major advancement compared to the conventional power transformer. And then we can have the services. All of these actually is one of a different paper, because you can really do many things. Once you have total controllability of voltage, of current, harmonics in the low voltage stage, you can really do a lot. And today we're going to see an example of this. So, as it is described in this slide, it is simply one of the several possibilities, because nobody forces us to say that the three stages, they have to be controlled separately. Actually, we saw it yesterday during the simulation. So the three stages, they are like communicating with the power exchange. If the power increases here, this voltage will go down, this controller will charge this capacitor, transferring power from this capacitor to this other capacitor. So this capacitor will go down, this controller will detect it, it will increase the current reference. That will increase the current in the medium voltage grid. So there are so many stages, so many passages that, of course, this is not going to be fast. It's a simple implementation, but it's not going to be fast. So there is huge room for improvement for control of a three-stage power converter. But for at least this, let's say, simple implementation allowed us to realize a fully working prototype of solid-state transformer and to test everything. Okay. So, in a very general, I have more slides, I can give you the paper. Actually, all of this is even discussed in the scientific literature. So, the way we implemented the control for the medium voltage grid, we have a current controller. These are the current control in the DQ reference frame, so in the synchronous reference frame. And we have an outer voltage control, a PI regulator. This is what we saw yesterday for the dual active bridge. And then we can have what I was telling you before. We have active power and reactive power. So the active power controls the power exchange between the three stages, but the reactive power can be used to provide additional services. One of the services is the voltage support in the medium voltage grid. If the voltage goes down, we increase the reactive power injection or absorption to lift the voltage up. Is basically what a STATCOM does. So sometimes you are forced to have a big power electronics equipment like a STATCOM, so static compensator, that is basically doing what for a current control power converter comes natural. Controlling some current, controlling some reactive power. Again, it's just a proposal. Of course, you don't need to use the DQ reference frame. You can use the stationary reference frame, so proportional resonant controller. You are not forced to use PI. You can use predictive. And again, so many degrees of freedom. think that this okay. Then, for the low voltage converter, what we saw yesterday was a proportional regulator, a simple proportional or proportional integral regulator. Yeah, this is really one of the basic steps. But once we really start digging into how a low voltage converter should be done, there is a vast literature related to the uninterruptible power supplies, because this is what an UPS actually does, is creates some stable grid supply when you have no grid. So in order to have a nicer waveform, we need to have a capacitor, LC or LCL filter. Capacitor and inductor, they can resonate, and this is exactly what we saw yesterday, that we tried to increase the gain of the voltage controller, but then it started to oscillate. So in an implementation for this control, and also what you will see in the simulation, that simulation file that I made some days ago and will be distributed, there is a current control, an inner current control. So in this case, the feedback is on the inverter current, but it is just one of the possibilities. The feedback for the inner current control can be the capacitor current, the grid current, can be any current. And to have some nicer waveform, usually we can adopt resonant controllers, for sure one at 50 Hertz. But what we didn't see yesterday in the ideal simulation, because we had a resistive loads are very nice, and unfortunately, the grid doesn't behave as a resistive load. The grid has a lot of power electronics converters with diode rectifier, with harmonics. So all of these electronic equipment, also many transformers, the transformers, they saturate, so they inject harmonics into the grid. Yeah, basically the low voltage grid is a very nasty environment. So to make sure that the power supply is a nice sinusoidal waveform, you usually have to compensate for all the higher order harmonics, adding more and more resonant controllers at the different harmonics. So this was a possibility. Of course, not the only one. You can use predictive, you can use repetitive control, you can use many kinds of controller to achieve the same objective. What I wanted to stress is that the grid is really a non-linear environment. So ultimately is our fault, is the fault of the power electronics engineer, that to shrink everything, to have higher efficiency and very low cost, then we made these converters that they pollute the grid. So really going in depth, so what can the smart transformer do? So this is just some partial list of things that came to our mind, because again, our imagination is limited, but if more people they start thinking of what a smart transformer can do, I'm pretty sure that there will be more and more services. So 3 stages. There can be services in all the environments. So in the medium voltage grid, for sure we have the voltage support. In the case of a fault, this is something very important in the power system. It is important in a distribution grid, and it is important also for an aircraft. We really have to consider what is happening in the case of a fault. If we have a fault somewhere, usually the voltage will go down, and what do? Do we disconnect? Do we stop giving the power supply? Well, of course not. So testing what a converter that is like a grid forming or grid interactive converter does when we have a fault in the grid is absolutely necessary. It's necessary in the distribution grid and is even more necessary in a fail-safe, in a safety-critical environment like the aircraft. So one of the things that a power electronics converter can do is once you have a fault, the voltage goes down, so you support the grid by injective reactive power. You can also compensate for the reactive power because now we have a conventional power transformer. If you take a conventional power transformer, medium voltage to low voltage, well, it operates as a transformer. So the reactive power that is in the low voltage grid is transferred, is taken from the medium voltage grid, magnetizing current. So a medium voltage transformer does not behave as a pure resistive load. If you want this to happen, then you need to have a reactive power compensation. But for a current controlled converter, this comes for free. Then, of course, power quality, you can compensate for the harmonics into the grid. You can really do a lot once you have a completely controllable power electronics connected to the grid. There are so many areas you connect. For the DC part, there is for sure the availability of the medium voltage and low voltage DC for the connection of the electric vehicles. You can also try to stabilize this DC network, because if you don't have the DC network, then it doesn't matter what is happening to the DC link capacitor. It's just there to provide some temporary storage. But maybe you are interested in controlling this. You are interested in having DC bus signaling, so shaping it to communicate to the DC grid some conditions, so what Tao was talking about yesterday. And for the low voltage, well, we have the total control over the low voltage frequency and voltage waveform. So we can identify the impedance. The reverse power flow limitation is the topic that I'm going to discuss next. We can have soft load reduction once we know the load mix. We can think of reducing a bit, performing this peak shaving. That can be very helpful for the distribution system operator to prevent the overload in some conditions. And of course, we can act a lot on the power quality. Now, I'm pretty sure that everybody that has ever realized a grid-connected converter coming from, I don't know, the undergraduate studies where we are told that the grid is a sinusoidal voltage. First time I connected the oscilloscope and I saw this trapezoidal voltage, more or less, very, very flat top. Then I went to my supervisor and I told him, hey, is there a problem with the oscilloscope? Because it's not sinusoidal. No, it's fine, it's fine. So the grid in a weak grid, so weak means with a high impedance, is really sensitive to this nonlinear and harmonic loads. So you're expecting to see some sinusoid, actually you see something with third, fifth, seventh harmonic. So it would be already a good service offered by solid-state transformer, the power quality control and power quality improvement in the low voltage grid. So, what is a reverse power flow? Well, it means that the power goes in the other direction. Okay, so why is this a problem? Let's imagine this scenario. We have a lot of distributed generation, and usually we install this distributed generation, we can, not usually, one of the possibilities to install the distributed generation, like a PV field, can be in the low voltage grid. Or if we have a neighborhood and each house has a PV power plant on the roof, then this is some usual scenario. In the majority of the time, the power produced by the PV is locally consumed in the household. Or if nobody is at home, this power will find some way maybe to some other houses or some local companies, some air conditioning system. So this is the usual, so this is what happens. There are situations that, again, can be caused by usually a mix of coincidences, but again, there is a certain probability that this happens. The power doesn't find its way. So I have in the low voltage, let's just imagine this. Italy, summer, everybody's on holiday, and I have a neighborhood with perfect clear sky and perfect irradiation. The PV is producing the maximum power it can, and nobody's at home. Well, what I said yesterday, the grid is in constant balance. So the power finds its way. So if it doesn't find its way in the low voltage grid, at some point this current will get to a transformer and it will just go to the medium voltage grid. So let's just say, usually what is happening is that in the distribution, so I have the high voltage transmission transformer. Voltage is 1 per unit, of course, is in per unit because all of these are different voltages. In power system, things are represented in per unit because it's more clear, because I cannot really compare a 400 volt with a 110 kilovolt. So the power is transferred from the high voltage network to the medium voltage. So because the grid has an impedance, inductive resistive impedance, I will have a voltage drop, is the standard equation, voltage equal voltage at the generator minus Z times current. So as long as I move down to the medium voltage distribution, the voltage will go down. Then I am here at the medium voltage to low voltage, and at the medium voltage to low voltage I have some distributed generation. So actually this point should have been here. They got a bit misaligned, but let's say as long as the power goes here, so you can imagine the current, the voltage goes down, but if I have distributed generation, actually the current goes in the other direction, so the voltage from this point will go up. So it's a standard situation, it happens quite a lot. I have a photovoltaic power plant at the end of the line, and usually the voltage at the end of the line can be quite high because the power is going in the other direction. But in the majority of the cases, this doesn't constitute a problem because if I have a load here, this load will be powered, will be supplied both by the distributed generation and by the medium voltage grid. So everything is within the limits. How come? What happened? Because it's very annoying. Yes, but maybe. Sorry, because it's very annoying too. Okay. So this is what is happening if I have a lot of distributed generation, and the power produced by distributed generation is much higher than, well, than the local consumption. It means that this power will go here through the transformer and eventually find its way in the medium voltage distribution network. But when this happens, it means that this nice profile where everything is within the limit doesn't happen anymore. So in this case, I have a severe voltage violation. I have severe voltage violation in the low voltage grid, and I have voltage violation at the medium voltage transformer, maybe. So situation can get serious. It's not always bad, the reverse power flow. Actually, if properly managed, the power produced by the low voltage grid can be transferred through the medium voltage distribution to some other low voltage grid, averaging it out, so can be quite good. But we have to pay attention that also overvoltage can happen. And once we go above a specified limit, maybe the grid-connected converters, they are protecting themselves, so they stop injecting the power. They basically disconnect. So if this very big generation at some point disconnects itself, switches off because of an overvoltage that actually it has caused by itself but doesn't know, maybe we have a massive drop in the generated power. We are having a very big transient in the grid that maybe can cause a blackout. So it's not some trivial matter. So depending on each site, depending on the climate condition, on the irradiation, and also on the load profile, there is the probability of a power flow, of a reverse power flow. Then, once you have a reverse power flow, there is the probability that something like this happens. So, if this happens and we have a chain of disconnection, maybe we are having a massive blackout. Industries, they stop, the DSO has to compensate with a lot of money, the customer, also because if the industry, they stop, not only they stop, but they're not producing. So it is a serious effect. So what can we do? Well, this idea started because in Italy there was several years ago one of these massive events, and after that I think that the regulation said that photovoltaic generation, photovoltaic power converter, they had to derate depending on the frequency. So what does it mean? Well, it means that at some point, in the case of a light load, it is possible that the synchronous generators of the power plant, they are a bit in some slight overfrequency situation. This can be caused by actually many causes. But one of the explanations is that if I have a lot of generation, basically I'm transferring the power to the medium voltage grid. In this case of light load, I may have a slight overfrequency, let's say, and if I keep feeding into this situation, maybe I have an overfrequency. So one of the things the regulators they did is to say, all right, if the frequency increases, then you cut the power, or you start reducing the power. So it basically means that there is some droop characteristic when the frequency increases, the power is reduced proportionally. And this is basically in every PV power converter that is sold in Italy and maybe in Europe, because they're all the same firmware, I think. So the idea was we can exploit this by preventing the reverse power flow in the medium voltage network. So how do we do it? Well, if we know that the distributed generation, that it can be a PV converter with this specific firmware, that, by the way, these are commercial products. Commercial products are supposed to behave in this way, at least in the ones sold in Italy. If the frequency increases, the power goes down. So with a smart transformer, I am in total control of the frequency. So I can decide to increase the frequency of the whole grid to control the power of the whole grid. Okay, but how do I detect this condition? Because I don't want to disconnect the distributed generation, because if the distributed generation starts to be disconnected, then I might have problem of grid instability. My goal would be to try to limit the power as much as I can so that the PV, it keeps feeding, but I am preventing the problems in the medium voltage grid. So what I'm looking for is a control, is not some on-off. So the idea is that we have a DC-DC converter in the solid-state transformer. And if you remember, I said that the power controller can limit the power. One of the simplest approaches is to say, okay, the power controller doesn't transfer the power from the low voltage back to the high voltage, to the medium voltage. So the DC-DC converter can decide to operate with unidirectional power flow. So in this case, the DC-DC converter blocks the power, but the PV, or anyway the DG, is still feeding power. The power always finds some way. So it will charge the DC-link capacitors of the smart transformer. So, of course, the DC-link capacitor is there for a reason. It's there to provide reactive power compensation, it's there to provide the snubber for the commutation, it's there to provide some compensation for voltage sags in the medium voltage, and so usually it's quite big. Meaning, if we want a smart transformer to provide services to the grid, then we will have some fairly big capacitance, because the capacitor is intermediate energy storage that actually enables all of these services. So power is reversed. The DC-link capacitor goes up, and I can have a characteristic that when the DC-link capacitor goes up, the frequency of the low voltage grid goes up. I hate it. So in the distributed generation case, what do I have? I have some current controller, and then I have some voltage controller for the DC-link. So basically what we saw in the demonstration down in the lab, that there was the converter implementing some MPPT, and then, okay, there was the predictive control. This is a general scheme. It can be predictive, it can be anything, but this is the usual way that distributed generation is realized. Phase locked loop, so everything that a grid-connected converter needs. And this is what I was talking about. With the time regulation, the frequency, the maximum frequency is 51.5. Across Europe, they have similar values, 51, 50.5, 51.5. And the rating starts from 50.3. So there is this dead band where the frequency is like allowed to fluctuate. Then, if the frequency increases, the converter has to curtail the power. Then, from the smart transformer side, we already see that we have the voltage and current controller. And what we did yesterday in the demonstration was to give some voltage reference. We had 3 sinusoidal voltages. They were the reference voltage for the voltage control. Okay, who generates this voltage? Well, in our case, it was just a Simulink block. Actually, this voltage is characterized by a magnitude and a frequency. It means that I can control the frequency. I can say that I measure the DC-link voltage, and then I have a lookup table. If the DC-link voltage increases, then the output of this lookup table is a frequency that changes from 50 to 51.5. The integral of the frequency is the angle, let's say, there is the 2 pi factor, and this angle can be used to generate my 3-phase voltage references. So there is no communication in this. There is a lookup table in the smart transformer, and there is a lookup table in the DG system that in most of the cases is already there because many regulations, they have this already there. So the idea is to take advantage of this because I can prevent the power. So this lookup table is there because if the frequency of the grid is increasing, then I cut the power. So normally the power should go up to the medium voltage, cause the problem, and then I cut the power. With a smart transformer, I do this completely in the low voltage network. I don't cause any problem to the medium voltage network. By the way, I can also have a communication interface, and the grid, the control center, actually tells me, look, conditions are fine. You can allow reverse power flow up to 0.2 per unit. It's another possibility. But otherwise, I just say, I prevent completely the reverse power flow. So, where is the trick? Can this work? Well, when you try to implement, at the beginning it didn't work. Because this interaction, so the two systems, there is no communication. But they have a PLL, meaning the distributed generation has a PLL. So it means that there is a delay between the moment where I increase the frequency and the moment where the distributed generation is actually limiting the power. So we have to analyze with transfer function what is happening. Of course, the system is nonlinear, the PLL is nonlinear, there can be many aspects, so this is just some, let's say, an approximation. However, considering the dynamics that we are considering with some big DC-link capacitor, from what you have seen, the simplified analysis was matching very, very well the actual experiment. So we have a requirement basically on the bandwidth of the PLL. Okay, bandwidth of the PLL is what does it mean? It depends where we start, where we consider the input and the output. In this case, the PLL is with unity, is the PLL on the angle with the unity gain. You can have a look at the paper to find the model. If we consider to have because these values are kind of small, probably, but because these values are considered with the unity, with the per unit PLL. if we consider the one with the voltage, this would come like 300 Hertz. That is maybe more familiar for people who design the PLL, considering also the amplitude of the grid voltage. But this is just a modeling. So from what we have seen, this is the root locus of this whole system. So basically, the distributed generation as a input as a frequency. To get the angle, I have to integrate it. There is the transfer function of the PLL, all PLL of all distributed generation. So there is actually some variability in this. And the output is some current. Then the AC current that is flowing to the grid, okay, I have to remove some contribution of the load, but the integral of the current, because there is an S at the denominator. So this is basically the DC-link capacitor plus some coefficient. So I have many integrals in the system. I have the integral of the DC-link capacitor, I have the integral of the frequency, and I have the integral of the PLL. So we can already think that this system is going to be quite slow. But still, with reasonable values, the system, just like this, it is stable when the bandwidth of the PLL is above 5 Hertz. And 5 Hertz is some very reasonable value. Usually the commercial products, it's above 10. So with normal converters, this can be actually applied. So something that we have tried to do is to test it on a real grid. It's always very tricky to test it on a real grid. There are some universities that actually have a microgrid, or even big microgrid with several PV converter, wind turbine. Maybe they also have the wind turbine, some battery packs. Okay, this is good, of course. You can do many experiments if you have a system like that. Of course, you require some investment, you require space, so it's, not everybody can afford something like that. So we are pursuing some intermediate approach, let's say, that is based on the power hardware in the loop. Power hardware in the loop, it means that you still have power electronics, you still have power flowing, however, part of the system is simulated real-time in a real-time simulator. Real-time simulator, like in this case we were using RTDS. RTDS, yeah, it stands for real-time digital simulator, but it's actually the commercial name, or it's a product. That it is used for power system analysis to have real-time data. Real-time is actually the key word. The difference between the MATLAB simulation and a real-time simulation is that the real-time simulation, 1 second of simulation equals 1 second in real life. So we can really test our equipment like that. So this structure of the grid was implemented. So all of this is like inside a real-time simulation. We have photovoltaic converters here inside the simulation, real-time simulation. Then we have also a power interface where we are implementing this control of the smart transformer inside this space system, so real-time control prototyping, to see if this can actually work in some complex scenario. So what do all this graph means? So we have two cases, let's say 5 and 10 Hertz of bandwidth of the PLL. We have what we have to see is the power of the two photovoltaic generators. In the black line, we have some normal profile, let's say, meaning the variability of the photovoltaic generation. And what we want to do is to curtail, to control the power at some specific value. So in the black case, we don't have any kind of control, so the power of the photovoltaic can be whatever we want. In these cases, actually, because of how the grid was designed, we would have a reverse power flow. So we can see that, okay, even here, so this is the DC voltage that normally is at this level, and then because we are already in this, at the edge of the reverse power flow, when the power goes up a bit, the voltage goes up, it doesn't reach like the limit, but I can see that in this point, the frequency is accelerating. So the simulation is we are at the edge of the reverse power flow. If the power increases a bit, the DC link voltage increases a bit, triggering the change in the frequency. So this is like the sequence. Power goes up, DC voltage goes up, frequency goes up. So here, nothing happens because we are basically at the limits. But in this situation, where we would actually have some serious reverse power flow, then we are basically stopping the power at this point because the frequency reaches the steady state. This is not out, so this is 50.5, so the limit was 51.5, so this is actually control, it's not saturation. The controller finds the right frequency to keep the DC bus at a specific point, and we are controlling the power. So it works. With 10 Hz of PLL, it works. If the bandwidth is a bit lower, then we are in this bouncing behavior where the system is like too slow. Too slow, it means that I see that the DC link goes up, I increase the frequency. PLL is slow to react, I keep increasing the frequency because the DC link voltage is still going up. Then at some point, the PLL detects the frequency and starts reducing the power. But I have already, my frequency is already too big. So power is going down, frequency is going down. So we just have this marginal stability behavior where the system is not working, let's say. It's not unstable because anyway there's saturation, but of course something like this is not acceptable. Here I have the frequency of my grid that is totally oscillating. Something is going to trip. I'm going to have power with this. So the idea is quite simple. Basically, I am accelerating the grid to emulate the behavior of an overload of the synchronous generator. But nothing of this is really happening because I'm just locally increasing the frequency of the low voltage grid. Of course, we even tried it not just with the real-time digital simulator, but we also tried with some grid-connected converters connected together. One was implementing the distributed generation, the other one was emulating the smart transformer. And we can actually see what is happening. In the case, at some point, we are disconnecting a passive load. So before this instant, everything is all right. There is no reverse power flow. This instant, I disconnect a passive load, meaning that the distributed generation is providing more power than what is needed. So bandwidth 10 Hertz, DC voltage increases, frequency increases, and then the system is stable. As we can see from the orange line, it goes down. 5 Hertz, I have this marginally stable behavior, let's say. 3 Hertz, no. 3 Hertz frequency goes up and then goes down. We don't see this exponential increase of instability because we have saturation and because the frequency cannot go below 50 Hertz. But this system is unstable. Of course, at this point where we are in saturation, so linear analysis is not valid anymore, but it is showing very well that it cannot work if the PLL is too slow. And again, we found really a perfect match between the analysis and the experimental result. So, meaning it shows that the model and all the things that we have like neglected, the dynamic of the current control, the type of the current control. So in this situation, all our assumptions, they prove to be very valid because this is the 0, so 3 is unstable and 5 is marginally stable. So, how much does it cost? Well, if you have the smart transformer, it doesn't cost too much because it's just control. You are increasing the frequency within the limits. All of this is within the limits. Voltage and frequency, they are within the limits set by basically all international regulation. So nobody can say that you cannot increase the frequency. Actually, we get this a lot, that we are not allowed to increase the frequency. Yeah, maybe it is true. We should still test if the increase of the frequency, how electronic equipment, how machines, how transformers react to this modification of the frequency. However, we are still moving in the range of international regulation. So we are not doing anything too strange, but we are really preventing the reverse power flow problem that can cause massive loss of service. So if you can prevent even one, of course you should analyze the money, but if you can prevent even one of these reverse power flow and this blackout, well, you can probably afford several smart transformers. Main problem is basically the ratio between the energy storage that you have and how fast the PLL is. If you have a very fast PLL, then you can go by with a small DC link capacitor. If you don't, then you need to make your system a bit slower. How do you make the system slower? Well, by increasing the DC link capacitor. So, to actually write down the transfer function, the PLL operates as a third order transfer function because we have the PI regulator and we have the integral action. So we can see that if we have some small DC link capacitor, the effect is like having a slow PLL. If we have instead some higher DC link capacitor, some bigger DC link capacitor, higher values, then we are having the same effect as a fast PLL. So it's basically the ratio. If you have a lot of energy storage with DC link capacitor, then your PLL doesn't need to be super fast. And by the way, we don't have the control over the PLL of the distributed generation. So the smart transformer is interfacing with a grid that it doesn't know. The dynamic of the PLL and how fast this control is implemented in a commercial converter, well, we don't know. Because, again, it's not something that is specified by the regulation. when you want to sell a photovoltaic converter, you go through the process of certification, they do some tests. If you pass the test, meaning nobody will ask you which is the bandwidth and which is the kind of your PLL. So it is tricky because interfacing with power electronics converter whose parameters you don't know, well, then you really have to see how sensitive the system is. You have to do some sensitivity analysis. You have to take into account that you don't have the control of what the manufacturers they do. But anyway, 10 millifarad of capacitance at 800 volt is actually nothing crazy if we are talking about megawatt power converter. So there is still margin. Consider that 10 Hertz is some reasonable value for a bandwidth of a commercial PLL. This can probably work in a real life situation. And again, we are assuming that the smart transformer doesn't have any storage, meaning except for the capacitor. If we think that the smart transformer has additional storage, then it can be used also to mitigate this phenomenon. So, okay, this was also some commercial analysis because basically we were told, okay, but if you always prevent the reverse power flow, it means that the PV is not generating as much as it can. So you have to compensate the owners. And it is true. It is true. But anyway, having the probability of a voltage violation and how much power you are actually reducing, there was some financial study, and so basically it depends on the probability. It depends on the probability of a voltage violation in the medium voltage. If the probability is high, then okay, you are reducing a lot, but you're also doing quite good to the electrical grid. So for this, anyway, don't have much time for this, but it's one of the papers in the reference section. All right, so questions for this part, then we talk a bit about the medium voltage control. No questions. Nobody that is studying PV converters. I don't know, how is the regulation here in Chile for the frequency, which is the maximum and minimum frequency? 1%. Mm-hmm. Yeah. So 50.5. Yeah. Plus minus 1%. Again, there is still a lot of margin. Every country, of course, they have different problems, so they set the limits to. It's curious if you see the regulation. Some countries are very wide with the frequency, but very strict on like the DC current. Some are they don't care for the DC current, but are very strict on the frequency. All right. So we have analyzed the problem. Okay, actually, let's have a 5-minute break. I drink some water.